have basically a distinction between um, analog signal and the digital signal. What is analog signal? Analog signal is a set of discrete time signal and the continuous time signals. Digital signal is a signal which has amplitude discretization. Okay. Well, how you look at a signal and you have to decide whether the signal is an analog signal or a digital signal. What you have to check, you check the amplitude. If the amplitude is discretized, which means if there is a condition on the amplitude, if there are some constraints on the amplitude, you have to say the signal is a digital signal. Okay. Well, the moment I uttered a word called constraint, it does mean there is a condition, which means condition has to be defined by humans. All right. So if there is a human, basically we can also define a digital signal in such a way that as analog signal with much more human intervention will result in a digital signal. You put a constraints on the amplitude by the human intervention, so the signal will become digital. So more and more, if the human intervention is more and more on the amplitude axis, the signal will become more and more digital. Okay. Well, in this lecture, I want you to understand a fact that I want you to understand the correlation between the analog signal and the digital and the discrete continuous time signal and the discrete time signal. Okay. Well, why is it so? Why we need to understand the correlation between the continuous time signal and the discrete time signal? This is the question. The answer for the question is, when in the course of signal system, we will be dealing about all the properties that belongs to signals. All right, which means by mathematically, continuous time signals like sinusoidal signals, like step signals, unit impulse signals, all these continuous time signals, all these basic continuous time signals are easily they can be easily deal with mathematics, which means when you compare, when I define a property for a continuous time signal, the next question you ask is, what about the discrete time signal? Can the same property will be applied for the discrete time signals as well? That is perfectly sensible question to ask. And to understand that, you need to understand the correlation between the continuous time signal and the discrete time signal. Okay. Well, I want you to understand this. Let's suppose you have recorded a time variation in a graphical manner. So you have basically you have a continuous time signal. So you take samples and these samples are periodic. Periodic means they will repeat after a particular time instant. In this case, it is Ts. So what will be the frequency? So the time period. The reciprocal of the time period itself is frequency, Fs. So 1 by Ts hertz. And the moment we took a change, the change means AC. The change means it something changes with the time. The moment I utter a word called change, there is associated word called frequency. Okay. So the moment someone tells you something is changing, you need the next question you ask is at what frequency it is changing. All right. And the frequency. So it is clear that the continuous time signal that we have took has its own frequency, and let's suppose that frequency is FM. Okay. So the frequency of the samples is Fs. The frequency of the message signal is FM, and message signal, the signal that we have took is a message signal. So Fs is if Fs is greater than 2FM, so I have defined Fs is a frequency, our sampling frequency, which is greater than 2FM. All right. So I need to make sure the sampling frequency is greater than 2FM without any information loss. This is a prerequisite. You need to understand why it is so. Why we need to take Fs should be greater than 2FM. For this instance, let's take this fact as granted. Fs is greater than 2FM. So once we know Fs is greater than 2FM, you take the samples with Ts time period. So you take so you have a sample signal. Okay. Well, the moment I say a signal is sampled with sufficiently faster pace, it does mean we take the sampling frequency is greater than 2FM intrinsically. Okay. So we have the sample signal. Well, you see, to understand the correlation property, when the continuous time signal is rising, well, let's suppose we have two variables. Let's understand this even more. Let's suppose we have two variables in x1 and x2, and let's suppose for this instance they are random variables. Random variables means we can't predict, you understand, right? X1 and x2, alright? And let's suppose x1 is increased and and let's suppose xt is also increased. Let's suppose x1 is decreased and x2 is also decreased. This behavior can be characterized with a positive correlation. Positive correlation. Pardon me for my handwriting. If x1 is if x1 is increasing and x2 is decreasing, or if x2 is decreasing and x1 is increasing, this kind of correlation is called negative correlation, which is quite opposite to this particular scenario. Negative correlation. So in our case, what are the two variables that we are taking? A continuous time signal and a discrete time signal. Okay. And continuous time signal. Well, if the continuous time signal is increasing, the amplitude of the sample is also increasing. Alright, it's clear. If continuous time is dipping, the amplitude of the sample also dipping. Clear? It has peak. The continuous time signal has peak. The amplitude of the sample has also peak. Clear? Which means if continuous time signal is increasing, discrete time signal is also increasing. The amplitude of the continuous time signal is decreasing. Discrete time signal is also decreasing. It does mean is it a positive coefficient or not? Yes. Alright. So the correlation of x of t, which is a continuous time signal, and sample version of x of nts is a positive correlation. Okay. Positive correlation. Given that, what is the prerequisite? This is very important. Given that fs is greater than 2fn. Alright. What is fs? Fs equals to 1 by s. Alright. Which means we have a property, we have a time shift property. It does mean we have a time shift property. The time shift property will preserve in discrete time domain as well. We have a compression or expansion properties. It will preserve in discrete time domain as well. We have a scaling property. It will preserve in discrete time domain as well. We have a linear time invariant continuous time LTI systems. The properties will almost preserve in discrete time LTI systems as well. So the moment when we have studied properties for continuous time signals, we also know the properties of discrete time signals for the large extent. Of course, there are a little bit of variations. We will get to know about that. There are a little bit of variations, but we have. The moment we know all the properties about the continuous time signals, we also know the properties of the discrete time signals as well. Alright. So the moment we are going to, in our video series, when we are going to define some properties for the continuous time signals, most of the cases you can imply this for discrete time signals as well. Well, you see, we have continuous time signal with discrete time signals. Both sets we have. Why do we even need to define this correlation? Well, you see, in future we are going to discuss about the properties. All right. Well, all the properties are mathematical, obviously. The basic signals like sinusoidal signals, step signals, and impulse signals, all these signals, all the continuous functions f of t. All right. All these signals are mathematically feasible. They are easy to deal with when you compare with the sequence. I can't make a statement that sequences are tough to deal, but in Indian education system we are used with sines and cos, sin t and cos t's, step functions and impulse functions. We can easily deal with them when compared to the sequences. All right, so we take the easier method. We go and define any property for a continuous time signal, and the same property will apply for a discrete time signal as well. Alright. So the takeaway point is there is a positive correlation between the continuous time signal and the discrete time signal. So the moment I define a property with the continuous time signal, it also implies most of the cases. I'm not saying in every case. Most of the cases, the same property will apply discrete time signals or discrete time systems as well. Okay. Thank you.